as always, guys, so I began recording. As always, if you reveal your faces and if you participate or speak to me, it's much nicer. It's much easier for me to gauge whether you understood something. At least I can see your reaction maybe from this camera. Mostly I just see a black screen. I imagine you went watching Netflix, right? And they're just playing this on another computer. Poor old me talking to you. So we spoke about combinatorics last time. I just be sure that you understand how combinations are supposed to work, right? And just brief recap. If you have n students of which you want to select R, how do you count how many selections are possible? So the way we decided to carry out the calculation, we selected all the students together. We placed them linearly. They're numbered 1 through n, and we placed them linearly against the wall. And next to the wall, you have 2 trays. One tray is the select tray, and the other tray is the deselect tray. Okay, and then we just take a permutation, the n factorial permutations of all the possible students, how they can stand linearly. And then the first R are selected, the next n minus R are not. Now, because you can see that I can shift around all the R individuals here, so there are factorial individuals that can be shifted. They can be shifted, and n minus R factorial individuals ways to shift the individuals in the blue tray. I know that every actual outcome of selected and deselected corresponds to R factorial multiplied by n minus R factorial permutation. Do you understand what I'm saying? So a permutation is like a word. They are n factorial words. Each word is of the same length, right, on those numbers. So in terms of language, that means that each particular actual outcome corresponds to R factorial times n minus R factorial words. So because each actual outcome has the same number of synonyms, we can just take the total number of words and divide by the synonyms to obtain how many meanings. You understand? The total number of words divided by total synonyms is the number of meanings, and that gives us the permutation formula n choose R is n factorial over R factorial n minus R factorial. Clear? Of course, we know that n choose 0, there is only one way to choose nothing. Well, maybe we don't know that that's kind of arbitrary, right? But that seems like a good convention, right? N choose 0, there is one way to not, no, you just don't choose anybody, right? So the answer is 1. If that's what you want, then and you want the formula to work, you just write n factorial over 0 factorial n minus 0 factorial. So that forces you to have 0 factorial equal to 1. Good. And then I just gave a few examples. I don't want to repeat them. And we introduced the Kafka form for this. So we now know how to count combinatorics. And now for the future, for more complicated problems, I think you want to construct those boxes, at least mentally. And so the idea is the protocol would be that if this box represents the choices of individuals, they should be numbered from lowest to largest. And they should be then therefore listed in this box from lowest to largest. So if I selected individuals 1, 4, and 3, I do not list them as 1, 4, and 3. I always list them in order. I rearrange them from smallest to largest. Make sense? That's the protocol that we have over there. And well, we covered all those questions before, so I hope you understood whatever I'm skipping here. We only left with one problem that was, and maybe you thought about it. Has anybody tried to think about it and not look at my notes? So counting, you see, this was the problem, okay? You imagine, maybe not antennas, much simpler to imagine pawns. You have white pawns and you have black pawns. Black pawns are the pawns that don't work. White pawns are the pawns that, or the antennas that work, okay? So you have m objects that are defective, and you have n minus m objects that are functional. And the question is, how many linear orderings are there in which no two defectives are adjacent to each other? So you cannot have two defectives adjacent to each other. And you see, you might be, one major problem in combinatorics is to select the correct object. Okay, so what is it that you want to count? What's the correct object to be selected? Many people make a mistake by picking the wrong thing. So functional antennas in the solution will be represented by 1. So I cannot distinguish one from another. Those are functional. And you have n minus m of them. And zeros represent the dysfunctional antennas. You cannot distinguish between dysfunctional. Okay, so I am required to have the dysfunctional antennas separate. So here is what we actually end up counting. The trick is not to deal with the antennas, but to deal with the spaces between them. So you see, we have here space number 1, space number 2, space number 3, all the way. For each functional antenna, we have a space before and a space after. So altogether, we have n minus m plus 1 spaces. Make sense? And what should I say about this spaces? So obviously, you just have one more space because we begin counting from before and we end up just after the last antenna. Now, each space can be occupied by at most one defective antenna. So the problem reduces to picking. How many spaces do you think we need to pick from them? So each space potentially can be occupied by only one defective antenna. So we have n minus m plus 1, choose what? Yes, thank you. Choose M, absolutely, right? You need to have specifically, you need to have M of the spaces occupied. Good. And that's the end of this lecture. Let's move to the next one. So binomial theorem, pretty important topic. Okay, so you have learned foiling from quite a while ago, but maybe you have not noticed some particular interesting pattern about foiling. So for example, suppose I want to FOIL A1 plus A2 multiplied by B1 plus B2 plus B3. What ends up happening? If you think about it, so I have all combinations from first parenthesis with all combinations from the second parenthesis. So for instance, I have combination A1 multiplied by B1, A1 multiplied by B2, A1 multiplied by B3. That's where first parenthesis contributed A1. And I have the same thing when first parenthesis contributes A2, right? All possible combinations. So you end up having a sum. And in the sum, you have, you can see two boxes, right? So this first box contains either A1 or A2. The second box contains either B1, B2, B3. And that right away tells you how many summons there are, how many terms you end up, right? So how many are those? By the basic principle of counting, 2 multiplied by 3, 6 in this case. All clear? So each AI, B sub j occur exactly once. Now it's very annoying to expand a longer product like the one I have over here, but what ends up happening, right? So the product ends up being over all possible sums, where first parenthesis contributes either A1 or A2, second parenthesis one of the B's, and third parenthesis one of the C's. So in this case, you can see how many possibilities are there, right? First is 2, second is 3, next is 4. So it's 2 times 3 times 4 possibilities. And that means the number of additions you perform is 2 times 3 times 4. Good. Now, this is supposed to help us to expand x plus y to the power of n. That's the binomial theorem. How do I carry out this expansion? So I put here the index under the x, but maybe actually I do it in later part. I should put it under the parentheses. If I have x plus y squared, I have one parenthesis, so parenthesis subindex 1, and second parenthesis subindex 2, okay? And the summation will be carried over all possible combinations from one term from parenthesis 1 and one term from parenthesis 2. You understand? So if I do not group similar terms together, I should have 2 times 2 or 2 squared combinations. Do you all see that? Because I have, let's say, for example, this x from first parenthesis with x from second parenthesis, y from first parenthesis with x from second parenthesis. All those combinations will occur exactly once. So then I can group them together. I clearly see that I can group them, let's say, by how many x's we have. So y squared means I have no x's, right? Both parentheses contributed a y. xy means that one parenthesis contributed x, the other parenthesis did not contribute x, and x squared means each parenthesis contributed an x, okay? So here it's pretty simple, right? You can see how to calculate it, right? So y squared means that first parenthesis gave us y and second parenthesis also gave us y. So there is only one possibility. Now for xy, I have two possibilities. Either first parenthesis gave me x, second y, or in reverse. First parenthesis gave me y and second gave me an x. So that's what I wrote over here, okay? And finally, for x squared, there is only one possibility. So here is how the grouping was done. Make sense? I just group them. Once I expand them, I have 4 terms, but I can collapse some of those terms together. And that's what you do when you write it in simplified form. So how am I going to do that in general with x plus y to the power of n? If it's n is bigger than or equal to 2, then of course, you see I have a bunch of parentheses, 1, 2, all the way to n, okay? And so let me see if you understand. Please write in the comments how many summons do I get? How many terms do I end up summing if I do not simplify those terms? Okay, you understand my question, guys? Most of you appear to be hiding. If you could, guys, again, show me your faces and speak to me. Show me that you are here. Maybe you left. Okay, what about the rest of you guys? What do you think? Interpret has answered something. What about the rest? Okay. And the rest? Melissa, Stephen. Thank you, Bowen. Thank you, Sandy. You all agree? Wonderful. All right, speak or type, guys, so that this way at least I know someone is alive on the other line. So what we have here is, again, 2 possibilities times 2 possibilities times 2 possibilities times 2 possibilities. You sure you absolutely get it, right? So because each parenthesis contributes only 1 term, right? So we have all those combinations. We have 2 to the power of n possibilities for the summation. Now, we would like to group them based on the powers of x. So here I have x to the 0, right? So some of the terms don't contribute any x, right? So y to the n, which means that each parenthesis contributed a y. Y to the n minus 1 times x means that all but one parenthesis contributed a y, and so on, right? I just list by, let's say, the increasing powers of x, right? So how many, I just group it. Do I have an x? I don't have an x, then I have once x, then I have twice x, all the way until all the parentheses contribute x to the n. And that's simplified term. I cannot go beyond it, okay? And if you took calculus, remember, we didn't use, actually, I tried to avoid using the binomial theorem because I don't go through combinatorial arguments, but we can use this to prove the the power rule for differentiation, right? We need to know how to expand x plus y to the n. That's one way to do it, or factor a difference of n powers, right? Shotaro, you remember that we did this way, right? We factor difference of n powers. This is now the binomial theorem. So the question is, and let's see if you can figure this out without me mentioning it. I'll just do it before. What's going to be the coefficient next to some general x to the k, y, n minus k, right? So that means where the general term is where x, we have k of them. Maybe k is equal to 0, 1, 2, 3, the general term. You can clearly see that when x is raised to the 0 power, there is only one way to do that because each parenthesis contributes exactly y. There is only one way to accomplish y to the n, right? But let's say for the next one, for the next term, x, y to the n minus 1, how many ways are there to get this exact combination? And that would be how many additions we have, right? How many ways was this, could this term have been created? You can type in the comments. So one person says 2. Do you agree, guys? There are only 2 ways to get x times y to the n minus 1. Only 2? So Naomi, you say 2 to the power of n minus 1. Any other takers? Well, good that I asked this question, right? It's very good that I did not just go through and assume you know it. You have to picture very clearly what's happening here, right? So you all, or most of you, it seems, you said all the number of terms is 2 to the power of n. What was that 2 to the power of n? They're not all distinct terms, right? So 2 to the power of n means here I can decide either x or y, right? So that's why I have a marker, right? They're not really distinguishable, right? The markers are erased, so once I multiply them out, some distinctions disappear. Do you agree? So let's look at the very simple case over here. Do you see why do we simplify it as x times y, right? If we have the marker below them, they are not the same. We have x1, y2 or y1, x2. You see, the markers make them distinct terms. But once I erase the markers, I can collapse those terms together. So if there are no markers below them, that I can simplify. Make sense? So it's like I can first assume they are distinct objects, and then I have, in this case, just 4 possibilities. But once I see that I cannot tell apart one x from another, and y and y from another, I can collapse and simplify. So there are 2 to the n different summands, assuming I can distinguish which x came from which parenthesis and which y came from which parenthesis. And each parenthesis contributes exactly one thing, either one x or one y. Make sense? So my question is, guys, in general, right? How many terms are there for y to the n? You see that there is only one way to do it, right? Because if I have y to the n, it means each parenthesis contributed a y. That's the only way it can happen. Now, for the second term, x times y to the n minus 1, how many ways can I create this term? Notice the x, you might think about it this way. Simplest to focus on the x, right? Because what does x times y to the n minus 1 mean? It means that one parenthesis contributed x, all the remaining parentheses contributed a y. That's the only way that could have appeared. Exactly. In Depret, the answer is n. Why? Because look at it, guys. Either it came from parenthesis number 1, the x, and the rest came, the rest were just contributing a y, or it came from parenthesis number 2. In other words, we see x2, and then we had y1, x2, you understand, right? And everything else afterwards is y. Or the x came from parenthesis number 3, or it came eventually maybe from parenthesis number n. So there are exactly n terms that will produce, n different terms in the sum that will produce x times y to the n minus 1. Before I move on, please write in the chat if you understand. If you have questions, speak out or write up the question. Wonderful. And then let's see what can you do next, right? So I'm not sure if it's going to be, to me, it seems from there it's as easy to jump to the general case as it is to solve the next term. The next term would be x squared y to the n minus 2, which means what? Which means 2 parentheses contributed x, and the rest of the parentheses contributed y's. Okay, but I don't see, in my mind, it's not easier or harder than the general case. How many ways are there in general if I just have x to some power, y n minus k, the complementary power? Of course, they add up to n because the product represents the contributions from all the parentheses. The fact that it's k plus n minus k means that each parenthesis has contributed something. Make sense? That's why the powers add up. How many ways are there to to create this term. N, okay, what about the, so everybody says that, guys? It's n choose k. The answer is n choose k. Do you understand why it's n choose k? Because what are you doing here? You see, you're thinking to select, so what does it mean? This means I selected exactly to x, let's say x represents selected, y represents not selected, let's say, right? So if I think this way, if I have n parentheses, exactly k of those parentheses were selected to contribute the x, and the rest were not selected, which means they contributed a y. You understand? I use this analogy. Does it make sense? So each parenthesis is like a student. That's another thing. It's analogous to class roster. So each parenthesis is like a student, and let's say x means the student came, y means the student did not come. Let's say, so this is the coefficient next to x to the power of k, y to the n minus k corresponds to the number of possibilities in which k out of the n students attended the course. Make sense? So this is, in particular, in this case, it means exactly k of the n parentheses were chosen, and chosen means they were selected to give away an x. Good? Type in the comments if the explanation is understood, and if you get it's n choose k. It's very important. It will be later binomial theorem or for probability. But all those things are very important. So not arbitrary, right? You see it perfectly. I hope so. Okay, so that tells me what is the formula in general. You understand? Because then I just sum up over all the possibilities. K is either 0. 0 means no x's were contributed, all the way to n, in which case all the x's were contributed. So the answer is n choose, so it's summation k0 to n choose k, x to the k, y to the n minus k. Okay? And what this means, in case you forgot the Riemann notation, that means n choose 0, x to the 0, y to the n choose 1, x to the 1, y to the n minus 1, and so on. Okay? So that is the general formula for expanding, for expanding x plus y. So let's try to just be sure. Let's have a comprehension check, guys. Right? So your goal here is x plus y to the 4. I want you to tell me what is the coefficient next to x squared y squared. Just calculate it and let me know what that coefficient is. You can type the answer simplified in the comment. That's very good. So coefficient is 4 choose 2. Why is it 4 choose 2? Because what do we have here? We have 4 parentheses, and 2 of those parentheses are chosen to contribute an x. And the remainder, of course, have to contribute a y. Make sense? That's why it's and here you see I already altered my notation, maybe because the x's are not distinct. It's really the parentheses that are selected. And here so the answer is 6. Here I actually listed them out in case you are confused, right? You see that? So just to be sure, you see, if I have two x's and two y's, it could be that first and second parentheses contributed the x and the rest contributed the y, or maybe first and third parentheses, or maybe first and fourth parentheses contributed the x's. That's why you have all those possibilities. But once you simplify it, you do not see the difference between an x and a y. Good. Wonderful. Strange. All right. Moving on. Here is your next task, guys. Let's see if you can do it. We will wait a little. Comprehension check. Your goal is to find, in simplified form, what is the sum of 8, choose 0, plus 8, choose 1, plus 8, choose 2, all the way to 8, choose 8. You understand? So you have an increasing order of what you have below the 8. 0 all the way to 8. I want to know, in simplified form, what is that sum equal to? Okay, two people have an answer. But the rest of you? Wonderful. Wonderful. So you get it. We'll do it maybe two ways. Exactly. Bowen, we can set x equal to 1 and y equal to 1. Thank you so much. So one way to solve that is just by pure arithmetic, right? We recognize that this is part of the binomial expansion for something to the power of 8, because we have 8 choose 0, 8 choose 1. That's something we have whenever we expand x plus y to the 8th power. But here, x and y can be picked to be 1, right? So observe that we can do is this way. We can just say 1 to the power of k times 1 to the power of 8 minus k, which is obviously 1 plus 1 to the power of 8, which equals to 2 to the power of 8, which is, I mean, that doesn't matter, 256. Good? That's solution number 1. I just want to mention solution number 2, because you see, it's always good to think about combinatorics, right? You think, here is recognition that it's part of the binomial theorem, and that's wonderful if you recognize it. But another thing that you want to train to do is to recognize that perhaps there are many ways to count the same procedure. You wonder, you ask yourself, can I figure out, or can I come up with a story to explain what has been counted here? What was somebody counting? Okay, make sense? So you see, when you have combinatorics, somebody might have tried to figure an answer to some particular counting problem. So what might somebody be counting? Well, suppose that I have 8 students, and the students are listed as student 1 through student 8. Okay, so what does 8 choose 0 mean? Anybody can tell me what 8 choose 0 means? If I have 8 students, that means what? Well, not the number. I'm asking what it means, right? In terms of the counting, right? So I said I come up with this analogy that I am counting something, and I have 8 students. What does 8 choose 0 represent? If would I be happy if I see 8 choose 0, or would I be upset?
I think it's that all the students are there.
Oh, the opposite. Well,
Oh,
you
they're
can
all
define
absent.
it whichever way. It's possible to say that. If you prefer, you can. You're an optimist, I think, right? Or you want to cheer me up, because no, the students are never there, right? It's like I'm sitting there, my finger swells, right? It's already twice its size. Why? Because I write those stupid notes. I write those stupid notes. I scan them. I present them, a tremendous peril to my existence, but nobody comes, and I get very angry, right? So that's exactly what this represents. It represents that no person came. Right, so all the possibilities, like nobody came. That's why the answer is one. There is only one way where nobody comes. Now, what is A choose one? That means one student came. Yes. So the answer A choose one is 8, because then I can list the possibilities. Student number 1 came, or student number 2 came, or student number 3 came. Is, and the rest did not, right? And etc. You understand? So I have piles. Those are like my attendance rosters for all the possibilities, right? So I might have printed all the attendance rosters for all the possibilities, and this is just one paper in which the attendance roster is filled with zeros for all the names, and this is the attendance roster in which I see 1 and everywhere else 0. And this is the attendance rosters in which I see a printing of 1 twice and everything else is 0. And the last term is everybody came. Okay, so that's the way the attendance roster might have looked like, right? So here this is just divided into piles for different circumstances, for the eventualities that nobody came, eventualities where 1 person came, etc. Right? So if I add all those piles, it's the same as the number of ways to fill out this document. And the way to fill out this document is 2 possibilities for student 1, either 0 absent or 1 present. Either 0 absent or 1 present for 2 and onwards, right? All the way to 8, either 0 or 1. So it's 2 to the power of 8. Make sense? So both parts are good, but you see, there are many very interesting problems that you can solve extremely simply if you realize that you have 2 correct ways of counting. So one does not have to be easy way or hard way, but if you have 2 ways that count correctly, you can just say that because they count the same thing, they must be equal. And that's called the combinatorial argument, or proof by a story. Because you assign meaning to what is done here. It's not just some arbitrary numbers, they have meaning. Good? And this is just following this explanation. All right, Melissa, have a good one. Okay, so here, since we already spoke, so in general, this is the situation. 2 to the power of n can be written as n choose 0 and plus n choose 1 all the way to n choose n. Make sense? Because 2 to the n means the total number of possibilities for selecting students up to n to attend this course, right? So assigning each zeros or ones. And that's the situation where everyone assigns 0. This is the situation where only 1 is assigned the mark 1 and everybody else 0. And the final is the situation where everybody is assigned the mark 1. Okay, and here is a useful identity. Okay, let's see if you can figure out the story. Maybe it's kind of like this out of the blue. It's a bit difficult, but it ends up being true that n choose r equals to n minus 1 over r minus 1 plus n minus 1 choose r. Good. All right, so tell me why this formula is true. Can you come up with a story? So some people will start doing calculations, but calculations are very unenlightening and very tedious. Right? Why would you right away look at it and say, aha, I know what it's counting, and therefore I know this formula is true? It's of course a little unfair that I ask you on the spot, right? Maybe it's hard for me to judge how long it would have taken me to figure this out because, you know, time flies. But once you are more comfortable, you start recognizing such possibilities much faster. You see, your goal is to try to figure out, it's like a riddle. That's why I enjoy it, right? It's like, what might somebody be counting here? So this is like a riddle. Somebody is expressing possibly some particular affinity, or, well, perhaps let me not torture you. Let me tell you what it is, right? All right, so suppose that in a particular class, there are n individuals and one individual is especially important or special, right? His name is Jimmy. So you see, we are going on a field trip. And on this field trip, I cannot pick all of the students. I need to pick exactly our students, okay? So this represents the number of possibilities of selecting R out of the n students that will go to the trip. Make sense? Now, if you understand this, let's see, what might this represent, guys? Can you figure it out? Again, the focus is on the special student Jimmy, right? What does this represent?
Would it be that since you already selected Jimmy and you already knew that you're bringing Jimmy, like you take one less from each so that you can take out
Jimmy? So this part means Jimmy is in, right? I'm bringing Jimmy. This is how many possibilities there are when I'm bringing Jimmy. So if I'm bringing Jimmy, I need to bring another R-1 individuals with Jimmy, and I no longer have access to Jimmy, so I have n-1 individuals remaining. Make sense? And so what is the second represents? What the second bracket represents?
If you don't bring him?
Exactly, Naomi, brilliant. And this is just, you don't, right? So this means they're not the same size. I'm not claiming that those piles are of the same size, but this is the pile of documents in which Jimmy was picked, you know? So what I imagine is I truly imagine that, and hopefully it will get easier for you. See, I imagine here a bunch of documents, right? And there is a pile of documents in which Jimmy is listed as number 1. In all of them, Jimmy is number 1. So maybe we have, sure, we must have. We had an example with not quite this example. We had something about people that are fighting or not fighting, right? So again, right? So this is the pile of documents in which I see the number 1. You see, I see codes, and the codes are all arranged in a box. There are letters, or are numbers to be precise, and the numbers are arranged in increasing order. So this is the document that starts with the number 1. And this is the document that does not have the number 1, or a pile of documents to be more precise. Those are 2 piles, piles that have number 1 and piles that do not have the number 1. Clearly, the sum of those 2 piles will be the total sum of piles. Okay, make sense? This is what I mean by my document. You understand? I imagine a bar, and each piece of paper, each document has this bar, and in this bar I have to put, or I have to list the students from the smallest integer student to the largest integer student that I bring. So this is the situation where Jimmy is in. You see the number 1. So Jimmy is in. Student labeled number 2 is not in. Student labeled number 3 is in, and all the way to student up to R+1 is in. Understand? So this is my document, one document in which Jimmy is in. So I sort into one pile documents that begin with 1, and I sort in the other pile documents that begin with the number 2 or higher. So this is why we have this plus that equals to n choose r. Make sense? And I did not have to do any algebra. Some people would start simplifying or doing factorial, and that is tedious and terrible, right? You just right away see that since they are counting the same thing correctly, that's the danger. You have to really be sure they're counting the same thing and they're counting it correctly, then they must equal. That's the idea. Okay, that's sometimes much nicer than in analysis because you don't have to go through all sorts of complicated things, and then it's like a story. Okay. So this is again illustrating what I just meant. Actually, I decided to, I'm sorry, I said Jimmy is labeled 1, but in these notes, I haven't read them after that. I decided to label Jimmy as n, to be specific, right? So this is the document that have n, and this is the document that cannot have n. It's the same thing, you understand? You can label 1 or not, but I decided here, that's the way the document will look for Jimmy. He is labeled as last, and this is the document that cannot contain Jimmy. Good? And you don't have to draw those pictures, you just have to think this way, okay, I think. You will see, especially from chapter 2, once we get to probability, it gets trickier and trickier, so you have to develop this facility. And you can write, when you submit solutions, right, it's not always easy to grade it, so try to give me indication of what you were thinking, so I know what was happening. So I would have written something like this, right? I would have said, Jimmy is a special student, this is Jimmy in, this is Jimmy out, okay? And then I understand maybe what you were thinking when you came up with this formula. Now, this brings us to Pascal's triangle. So Bowen is asking something. Is it possible to generate the identity to cases more than 1? Yes, it's actually going to be one of the comprehension checks. So good that you anticipate me, Bowen, thank you. So let's first go through the triangle, through Pascal's triangle, I'm sorry, right? You might have seen this structure before. It's a pretty popular structure, and it's very useful in particular for expanding the binomial. Okay, so the triangle is obtained as follows. You begin with 1 and 2 1s below, and then right below you write the following. You just have 1 2 1. You always start it to each row with 1 and end it with 1, and the middle term. So for example, how do I get this term, right? You see, I take the 2 terms just above it, I add them up, and I get this 3. Do you understand? I'm hoping because of the picture that my very poor wording is adequate. You see how this is done, right? So it's just first is 1, second row is 1 1. That would correspond to expansion of x plus y to the power of 1. Next row, you begin with 1, and then you put this sum of the 2 top terms that you put in the middle of them. You put 2, and you put 1, and then you have those 3. You start with 1. 1 plus 2 is 3. Then the next one is 2 plus 1 is 3, and then you end up with 1. You have this term, and you go on. Make sense? And you can generate, once you have the top row, it's very easy to generate the next row. Make sense? Everybody understands, guys? If you need more explanation, or just actually simpler, just say, yes, I understand. Right? Type yes, please. Okay, great. Thank you so much, guys. If somebody for some reason is lost, don't hesitate. Ask me right away. Don't worry. So why is this Pascal's identity so useful, guys? If you think about it, let's look at row number 2. Oh, sorry, row number 3. Row number 3, the first one represents 2 choose 0. The 2 next represents 2 choose 1, and the final one represents 2 choose 2. You understand? So in this row, I have 2 choose 0, 2 choose 1, and 2 choose 2. Now, what is this? This will the next row, the fourth row, should represent 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Okay. Let's see how I'm using that Jimmy identity. Right? Where is the Jimmy identity? That's why I'm adding up. You see? Look at how let's suppose that what I want to know is what is 3 choose 1. 3 choose 1 is the second term here. So this is 3 choose 0. This is 3 choose 1. What is 3 choose 1? 3 choose 1 is, according to Jimmy identity, the same as 3 minus 1 choose 1 minus 1 plus 3 minus 1 choose 1. Okay, which means it is the sum of the direct two elements above it. You see, because that is 2 choose 0 and 2 choose 1. You understand that this Pascal's triangle, each new row is constructed using Jimmy's identity. Make sense? Type yes if it makes sense, so I don't need to talk about it longer. If not, I will try to explain again. It's pretty cool, right? So with this, you can actually come up with the coefficient and also figure out n choose something recursive. Of course, if it's let's say 100 choose 70, you have to add a lot of things. You have to complete the triangle and go quite a long way down. Okay, but this then allows you to right away figure out what's x plus y to the power of 4. That would be the coefficient will be 1 x to the 4. 4x cubed, y, and onwards, right? So I can just put in all those coefficients, and I expanded, let's say, x plus y to the 4 very quickly without foiling, just right away. Make sense? Because those are the binomial coefficients, so I know I will have them here. I just put them where they belong. All right, and here is possibly, well, the question that that somebody already anticipated. The question that, well, so guys, can you come up with a combinatorial argument for the following scenario? Okay, you have n choose r multiplied by m choose 0 plus n choose r minus 1, n choose 1, and all the way until it's n choose 0, right? I go from r, I decrease until I go to 0, and I take elements from m here. So the question is to figure out what is this sum equal to. Well, the question is why 2? Naomi, right? Maybe 2, maybe not 2. You see, it's an abstract formula. It's you have n choose r, m choose 0, right? Plus n choose r minus 1, m choose 1, and onwards, right? So the question is, what is this summation? Can I simplify it or find another formula for it? What are we counting possibly? And just as you were thinking about it, you see people torture me. So somebody sends me riddles, right? I hate it because then I'm bothered, right? It's like somebody wrote me a hidden message with code and they are telling me to break it. I actually feel like giving it to you, but maybe it's an intimate, you know, message, who knows? Maybe it's your assignment, right? You tell me what's the code. I'll write one that's pretty silly. That's from a German fireman, of all people. This one is silly. That's but this is one message somebody bothered me with. This is pretty easy, you know. You can actually even Google it. So. But later. First, focus on this thing.
Could it be this is the combination of the how many students could possibly come to a class? How many students from two groups are coming to class? Something like that.
Well, that's very good thinking, Shotaro. So right, what might it be?
So the first one would be describing like, so our students come from this N group and no one comes from the M group, and then eventually be going all the way to, and no one comes from the N group, and many people come from the M group, but all of these would be describing, all of these would have the exact same number of students in the classroom at one point.
Good thinking, right? So you realize it could be generalization of Jimmy identity, in a sense.
Yeah.
And because in the Jimmy identity, one group was Jimmy and everybody else was in the other group. Right? So that's, I think, somebody was asking regarding a generalization. That's one, I think, generalization of the Jimmy identity. But if you realize that, what is the answer? What is that counting? Another way.
What is that counting?
In other words, what it equals to. I mean, I think you might have realized what it counts, but you know, what is it equal to then? Well, Chabeli, you have been quiet today. I hope you're doing well.
Just a little confused.
Confused? You see, don't ever hesitate whenever you're confused. If you have, actually, after the class is over, we can go over anything you like, okay? Or don't actually be shy from anybody. So Naomi, you got it, Naomi. Excellent. N plus M, choose R. Brilliant. Now let's view why it is the case. Okay, so here is the solution. We can imagine the following, right? So imagine that we have N girls and M boys in the class, and I invite R of those individuals to a field trip. Okay. Now, how I can what can I do? I can only, let's say this situation is only boys come, no girls came. Sorry, only girls come, but no boys came, right? And this situation is where one boy came and the rest were girls. And the final situation is, apologies, I mixed the categories. N is girls and M is boys, right? So you get it, right? So N choose 0 means no girls, only boys came. So the first thing, only girls came, no boys. Last category is only the boys came. And clearly that's the seed. So what did I do here? It's the same as just taking a subset of size R from the entire class, which is N plus M. It's the girls and the boys. Okay, does it make sense, guys? If yes, type yes. And if no, type no. And again, guys, you can always talk to me, right? Some of you are quiet. I don't think you believe me that you can talk to me. Because I bet I seem to you rather weird, right? That's why. You know, last semester, somebody suggested a Spanish book. I'm still to read it. Apparently, I am a major character in some novel. His name is Arkady, I think. Arkadio, I'm sorry, right? And it's called 100 Years of Loneliness. Yes, exactly, right? So if you are alone for 100 years, you know, you should actually see what happens to you. Good? If, guys, you are shy or anything else and you haven't understood something, please stay with me stay for office, we can discuss everything just with you if you don't like other people to listen to your solutions. But again, don't be shy. I was always thinking when linear algebra, I thought everybody is so smart, understood everything, and then I realized they knew nothing. They were just like, they're making smart faces, but understood nothing at all. All right, so you see, it's pretty cool, right? It's like a code, and when you realize what it means, it feels just so great, right? You understood what it means. It bothers me. So somebody writes me some code just now, and I just solved something yesterday. I don't have time for it, right? I have a lot of problems, lots of problems. Trust me, right? So where are we now? We finished with binomial, so we are at multinomial coefficients, correct? When is this class over? 5:50, right? So 6:50, correct? We have some time. Multinomial coefficients, okay? So 3 dragons have each kidnapped a princess, and then 10 brave knights are sent to rescue them. So 3 of the knights will be sent to the first princess, 3 to the second princess, and 4 to the smallest princess, to the last one. And now, assuming that each knight will be eaten by the dragon, right? How many destinies are there? And here are my dragons, right? Do you like them? So that's dragon number 1. He will like to have 3 knights, please. Dragon number 2 would like to have 3 knights, and dragon number 3 is a glutton. He likes 4. Okay, so those are the destinies. But I truly think when I think of this problem, I think of a song. It's a Russian song. So I would have played it to you, but maybe you would think that I'm even weirder. But the words there are: goodbye, Moscow. Your soul will always be with us. You understand the question, guys, right? So let's see if you can come up with a solution to this question. And the destiny here only simply means which knight. Destiny decided which particular knights go to which dragon. That's it. You understand?
Professor, can we see the question again?
Oh yeah. It's 10, again, you can remember it's 10 knights, 3 dragons. This dragon takes 3 knights, the second takes 3 knights, the last takes 4 knights. Okay? You have to distribute the 10 knights among them as the following way: 3, 3, and 4. Good? And destiny here just means, well, which particular knight groupings go to which particular dragons. That's what I mean by destiny. Good, good. That's Bowen, wonderful analogy. Yes, very similar to the previous question. It just generalizes it. Okay, so just in case that the others are still working, I'm just waiting a little to see what others would like to say. Okay. And if you finish with this problem, try to think about what I just wrote before, right? That's simple. But are we ready, guys? So Bowen, regarding that question, what do you mean? So so what's the answer? Yes, Naomi, you are correct, right? I thought, I forgot that G is the constant of gravity. So I realized a pig without a pi is G, but then I thought why what is it? I thought maybe alphabet, right? What, 9.8? I look into, if it's 8.9, it would be high. So I thought a pig without a pi is high. But somebody wrote a much worse thing. It seems like a message, you know, like a few lines, and like I just said, my God, I'm so curious what it is, but I don't want to bother with it right now. All right, guys. So let's work on this question together. So here is how I imagine it. Okay. So we align the 10 knights in a row, and then we put trays below them, right? So tray number 1 will be served for dragon 1 to eat. Tray number 2 is the dish for dragon number 2, and tray number 3, of course, goes to the according destination. Now look at it, right? So how many synonyms are there, right? So for each particular outcome, I can rearrange knights on tray 1 without bothering anything. I can rearrange knights in tray 2 and knights in tray 3. So that means that for a particular outcome, there are going to be 3 factorial times 3 factorial times 4 factorial permutations. So if you take 10 factorial and divide by 3 factorial, 3 factorial, 4 factorial, you get all the possibilities. Does it make sense? You see, because what I know is that there are going to be exactly 3 factorial, 3 factorial, 4 factorial permutations that represent the same outcome. Same knights go to the same destinies. Okay? And this is how you write the answer. You write it as, it's called a multinomial coefficient for reasons that we will explain below. But it is 10, choose 3, 3, 4. And when you calculate it, it's equal to 10 factorial, 3 factorial, 3 factorial, 4 factorial. And that's just an extension of combinations. You understand? It's just like generalized combination. Because you see, combination is, let's say, if it's just 10, choose 3, and then the combination can be also written as 10, choose 3, and 7. You understand? So those numbers add up to 10. That means those are their destinies. In combinations, you only have 2 destinies, so it's enough to specify just one. Selected and not selected are the destinies. Good? And this is the general situation. If we have R dragons, and we need to assign N1 knights to dragon 1 and 2 knights to dragon 2, all the way to NR dragons to dragon number R, and the number of dragons, of course, has to add up to N. Then the possibilities are, it's just N, choose N1, N2, and R. That means that this is assigning the distinct objects, the knights, to their distinct destinies, dragon 1, dragon 2, all the way to dragon R. Make sense? So that means distinct objects, distinct categories. And this is how many objects each category requires. They have to add up to N. So we have N factorial, and 1 factorial, and 2 factorial, all the way to N sub R factorial.
I have a question.
Go ahead, Naomi.
I just kind of looked at it the same way we did with like those pawn problems from the first day of class. Is it the
That's
same
similar.
thing,
That's
or is
very
it?
similar? The only difference is here, I mean, depends what you, so obviously they are very similar, very similar. The only thing is I can distinguish each of those objects, right? So that's why I don't want to confuse it. You can think of it. I think I know what you're thinking, but I think possibly the clearest way to imagine that is that all objects are distinguishable. So they're not exactly like the points, but well, you see that once they are on the trace, the distinction is no longer there. Perhaps
Okay.
if you like to imagine it this way, right? I actually imagine if I need to justify it completely rigorously. So I mean, intuitively, I think, okay, I put a particular permutation and I see that there are many rearrangements of the permutation. Those knights can jump around. Those knights can jump around as long as they don't switch the tray. Their destiny isn't changed, and those can switch around. And then intuitively, just like with the pawns there, you can see they're going to be 3 factorial, 3 factorial, 4 factorial. But in case I need to really justify it, I would print a document. In other words, I'll have a document for a particular permutation, and I will examine how many rearrangements are available, which we did as well for the pawns. Okay, so yeah, so hopefully that's clear completely, right? You can see exactly what happens, and that's the situation. It's 10 factorial permutations, but fewer meanings, because 3 factorial, 3 factorial, 4 factorial permutations correspond to one meaning. For any other meaning, the same number corresponds. That's why we can divide. When that's not happening, there are no easy formulas. It's not always that, let's say with the English language, some words have very few synonyms, some have many synonyms, so it's not so simple. Okay, good. So I don't think I should go into the expansion because we only have, what, 2 minutes, and maybe it will be too much to go, right? So I think we can call it a day, guys. If you want to, you can go. If you want to, you can stay. I will stop the recording, and if you want to talk about something, I'll be happy to.